the research you've been doing on virtualization, is that feeding into the work you're doing in Bromium?
Yeah, so really the story of how we got into doing this starts back in about the year 2000 when I was at the university with a number of students, and we started the work on the Zen hypervisor project. So the Zen hypervisor is at the core of Amazon AWS and many of the other infrastructure as a service cloud computing environments. It's the hypervisor which securely divides up a machine to enable multiple customers to be able to run on the same machine. And with the work that we did at the university, one of the things which we did fairly early on was to start working with the CPU vendors, with Intel and AMD initially, and really having conversations with them about what kind of features we would like to see in the CPU to enable us to do a more secure and higher performance job of virtualization. And of course, all the work we were doing at that time was focused on virtualization of servers, either in the enterprise or to enable cloud. But those exact same CPU cores which are used in servers are also used in all of the chips that are used in desktops, laptops, and many tablets too. And in fact, often those cores are available earlier in those chips. That's where it's the proving ground before they move into the server. So the net result is that from about 2009, any of the CPUs you've bought for your PCs, desktops, or laptops, desktops, etc., will have what's called the third generation virtualization extensions built into those cores. And on the desktops and laptops today, those transistors basically sit idle. No one's using that capability. But that's what enables us, your Bromium, to exist. We can make use of that virtualization capability to be able to create these new virtual machines for every task that the user performs. So if you were to look at my laptop right now, it's probably running 40 or 50 different virtual machines on that laptop using those hardware capabilities, so that every website I have open, every document I have open is in its own isolated environment. And then beyond that, when something is running in one of these virtual machines, we can actually stand outside looking in, observing the execution. And because we created this virtual machine for a particular purpose, to run Chrome or Internet Explorer or Word, whatever the application is, we have an expectation as to what it's going to do. So we can look at the execution trace, this black box flight recorder trace of everything it's doing, and if it does something different from what we expect, we know that something interesting has happened. We know that execution has diverged, therefore the input must have been malicious. So we know that that document was bad, that web page was bad. And then policy determines what happens next. But the way that most customers have the product configured is you just let the attack play out. You let the execution continue, at least for another couple of minutes. So that black box flight recorder trace captures the full kill chain of the attack. And we can stream that information to a management server in real time, and then perform analysis on it to pull out the interesting parts of the attack. So we can then present a visualization of it, showing which machine it was, who the user was, which website they went to, how they got there. Was it a link in email? And then how did the attack play out? What was the vulnerability? What was the privilege escalation method used? How did the malware try and persist itself? Did it modify files on the file system or the registry, the master boot record? Did it try and perform various anti-forensic activities to clean up after itself? We can see all of that and then see who's it communicating with, who's the command and control server that this malware is talking to. And we've been able to capture all of that very detailed threat intelligence without a machine ever getting compromised. There was no risk, there was nothing to steal, nowhere for the attacker to go, and we were able to collect all of that threat intelligence. And then as soon as the user clicked a link going to a different website or closed that tab, or perhaps the 2 minutes were expired, that virtual machine's thrown away and the system is back to a clean state. So it really is a very different approach to solving the problem, where we're saying trying to secure a web browser or Word or even Microsoft Windows, it's an impossible problem. We're talking about an attack surface of maybe 100 million lines of code, much of it created in the 1980s, where security was not really front and center of what they were thinking about at the time. And so you end up with this huge attack surface which is basically undefendable. the approach that we've taken is to say, well, let's not worry about securing that. That's an impossible problem. Let's just create a new instance of that entire software stack whenever we start a new task, and we can do that in just a few milliseconds to create a new virtual machine. And then we only have to worry about securing the CPU and the hypervisor. And that's a much smaller attack surface, 1,000, 10,000 times smaller, written in modern times, using all of the various tools that we have at our disposal, which weren't available to Microsoft when they were writing Windows. And then let's do a really good job of testing it. Let's have in-house pen test teams beating up on it continually. Let's have external pen testers being commissioned to beat up on it. And then now increasingly, let's interact with the community of security researchers, getting them to look to see if they can find flaws in it, because that's how we can really harden that code base. And it means that not only has an attacker, they've got to find a flaw in the application, they've got to find a flaw in the OS, but then they've got to try and break out the hypervisor or the CPU if they want to do any damage. And that's something which is much, much, much harder than doing it than escaping from an OS. And the more testing we have, the better job we can do of that, the more hardened and secure we can make the product.
So I'm curious, what are your predictions for the way security is moving forward over the next couple of years?
So I think that we'll see that detection-based approaches have kind of run their course. They've got as good as they can do, and that the machine learning and approaches like that can only get you so far. And then it's really a case of looking at other approaches, looking at isolation as a means of defending yourself against these kind of polymorphic threats that are able to morph themselves to avoid detection. And that's that kind of isolation-based approach. There are clear parallels with what's happening there. What we're trying to drive on the endpoint to the approach which is now being used in the cloud, and using a hypervisor to securely divide up the resources of a machine between different customers who don't trust each other and want to be isolated from each other. And it's effectively different tenants of the server. When I'm using my laptop and I have these different virtual machines, perhaps one that happens to be accessing Facebook, one CNN.com, and then one my banking website. They're effectively different tenants on my endpoint, my laptop, and we can use that same approach to isolate them, that same kind of virtualization technology, both on the server and on the endpoint.
So are you optimistic that the good guys are catching up with the bad guys, or are we always going to be on a kind of swings and roundabouts?
So right now it's clear that the attackers have huge advantages. It's the only tools that you have to defend yourself at a detection. The attackers are going to win with very high probability, but it doesn't have to be like that. There's been a lot of good operating systems research and security research, and even approaches like formal methods, coming from other areas of computer science, that can enable us to build far more secure systems. It's just those aren't the systems that we use today. The commodity operating systems and web browsers and all of these approaches haven't taken advantage of those techniques. Now, what we're able to do of using this approach of micro-virtualization, we can make it so you don't have to worry about the security of those applications or that OS. We only have to worry about the security of the chip and the CPU, on the hypervisor, where we can do a better job. We can focus our efforts around security. And I think in other areas we're going to see more use of those techniques that have existed and been created, and particularly with formal methods becoming more viable as a way of actually proving properties about systems. There's certainly hope that we can actually do a much better job in future, but all systems are vulnerable. All software has bugs. Even if you've proved it correct, it doesn't necessarily mean that the implementation is going to be fully robust. So there will always be problems, but we can make it much, much harder than it is today. And certainly what we would like to do is to make it such that if we could just wind the clock back 30 years, where if you wanted to perform industrial espionage on a company, then some guy, with a balaclava on his head had to, climb up the side of a building, open a window, climb in, and then pick a safe, and then make off with the plans. They had to put themselves at risk to actually steal that intellectual property. Whereas today, it can be done thousands of miles away with basically no chance of ever getting apprehended or even the attack being attributed to you. The cost is just so low now that it's happening all around us, and we need to try and make it, get it back to the time where someone did have to put themselves at physical risk to actually steal that intellectual property. That's the level that we need to be aiming for.
One final question. In the past, software developers were kind of creating software and then thinking about security almost as an afterthought. Do you think that's changed now, or are we still very much in that kind of bracket?
Well, I think people are more aware of security. There are companies, particularly some of the large companies like Microsoft, that have quite frankly had near-death experiences of creating software which has so many security issues that it just becomes a huge problem for them. And Microsoft, I think, were one of the first companies to really lead the way and say, no, we need to take this stuff seriously. We need to make it such that the new software we're creating is a lot more robust and secure than the old software. The trouble is that there's so much of this old software out there that it's going to take Microsoft 20, 30 or ever how many years to really be able to get to a hardened state. But other companies have seen that and are at least trying to build more secure software. But there are always going to be pressures for around developer productivity and all of the other pressures that folk have to ship software. And if security is an afterthought, that's a real problem. Security is something that really needs to be part of the design. You need to make sure that you are employing those principles of least privilege and other good design methodology to try and avoid security bugs from an architectural point of view. And then, of course, you need to do a good job of implementation. And there are, obviously, you can be selective in terms of what programming languages you use, and to help avoid whole classes of issue that could otherwise occur. And then, there are a lot of tools available today to help with static analysis and also dynamic analysis to help you understand the security properties. And then you should be using, obviously code review and fuzzing and pen testing and all of these other approaches. So it is possible to do a much better job than the typical security of a web browser or other application today. And as an industry, we need to be held account to do a better job than we are. And I think it's particularly concerning with now having connected cars and the Internet of Things, where the costs of getting it wrong are potentially much greater. We could there's obviously the spectre of cars running off the road, or perhaps even more seriously, power grids being turned off and us being sent back to the dark ages if we mess some of this stuff up. So it's something which the industry needs to take seriously, and everybody needs to be held accountable for the security of the software they supply.
Thank you very much.
Thank you.
Good stuff.